In this demonstration, I'm going to drop a magnet through a copper pipe. As you can see, when I drop the magnet outside the pipe, it falls very quickly, as we would expect. But when I drop the magnet through the pipe, it falls much more slowly. This phenomenon is explained by Maxwell's equations, which describe the relationships between electric and magnetic fields. One of the consequences of Maxwell's equations is that an electrically charged object feels an electric field pushing it sideways when the charged object moves through a magnetic field. In other words, when a charged object moves through a magnetic field, a sideways force is exerted on it, a force perpendicular to the object's direction of travel. Now, as the magnet falls through the pipe, its magnetic field is moving downwards relative to the electrons in the copper. This has the same effect as though the electrons were moving upward through the magnetic field. Since electrons are charged objects, Maxwell's equations imply that they should feel a force perpendicular to their motion through the magnetic field. In this case, the force will be horizontal because the magnetic field is moving vertically. So a horizontal force is exerted on the electrons in the copper, and that force causes the electrons to move in a circle around the pipe. But what happens when a charged object moves in a circle? According to Maxwell's equations, whenever a charged object moves in a circle, a magnetic field is produced. So the electrons produce their own magnetic field as they circle around the copper pipe, and this magnetic field opposes the field of the falling magnet, so the magnet falls more slowly.